Today, we're designing one of social media's most technically demanding features, a system that must process 14 plus million location updates per second at peak, calculate proximity in real time with geospatial accuracy, maintain persistent connections for millions of concurrent users, all while keeping location data secure and ephemeral, and it needs to work equally well whether you're checking friends at a coffee shop or monitoring crowds during a global event like New Year's Eve in Times Square. The problem is to design the Nearby Friends feature for social networks. Here are some good requirement questions to ask. How close is considered to be nearby? Can I assume the distance is the straight line distance? What's the DAU? Do we need to store location history? Do we need to worry about privacy issues? In this slide, we're looking at the high-level architecture for the Nearby Friends feature, which relies heavily on real-time location updates and efficient message distribution. Load balancer. At the front, we have a load balancer that directs client traffic to either the API servers or the WebSocket servers depending on the request type. API servers, these handle standard operations like managing friend relationships, profile updates, and general RESTful API interactions. WebSocket servers. These are critical for real-time communication. Each client maintains a persistent WebSocket connection to one of these servers. When a nearby friend updates their location, this is the channel used to push that update directly to the client. User and location history databases. We use these for storing permanent user information and historical location data, useful for audits or past activity features. Redis location cache. This is where the most recent location for each active user is stored. Each entry has a TTL to automatically clean up stale data, keeping our system fast and relevant. Redis pub chark subserver. This acts as a lightweight messaging bus. When a user moves, their new location is published to their personal channel. Each of their online friends' WebSocket handlers subscribes to this channel. Now, walking through the location update workflow, the client sends a location update to the load balancer. It's routed to the user's assigned WebSocket server. This server stores the update in the location history DB, updates the location cache, and saves the current location in memory for fast distance computations. It then publishes the update to the user's Redis pub sub-channel. Any WebSocket server handling a friend of the user, if that friend is online, gets this update via subscription. The distance between the sender and the subscriber is calculated. If they're within the search radius, the update is pushed to the subscriber's client in real time. Otherwise, it's discarded to save bandwidth and processing. This architecture is designed for low latency, high concurrency, and geo-aware messaging, which are all critical for building a responsive Nearby Friends experience. In this slide, we'll walk through the in-depth design of how the Nearby Friends feature works at scale, focusing on system initialization, caching, communication, and scalability techniques. Client initialization and location sync. When the client app starts, it establishes a WebSocket connection and immediately sends the user's current location. The WebSocket server updates this location in the Redis-based location cache and also stores it in memory for quick access within the user's connection handler. Then it loads the user's friend list from the horizontally scalable user database. It makes a batch request to the location cache to get the most recent locations of all those friends. Note, if a friend is inactive or their cache TTL expired, their location won't be included. For each friend with a location available, the server computes the distance. If it's within a predefined radius, their profile and location data are sent back to the client. Simultaneously, the server subscribes to the Redis pub sub-channels of each of these friends, so future updates can be received in real time. Redis pub sub mechanics. Redis pub sub acts as a lightweight message bus to route real-time location updates. When a user updates their location, their handler publishes it to their dedicated pub sub channel. All subscribed WebSocket servers belonging to that user's online friends receive this update and recompute proximity in real time. To manage scale, we use consistent hashing to evenly distribute channels across pub subnodes. It's a memory-light but CPU-heavy workload, the main bottleneck we're optimizing for. Each channel is independent and stateful. It remembers its list of subscribers. Friendship management. To handle dynamic social graphs, clients register callbacks for friend additions or removals. These trigger updates on the WebSocket server to either subscribe or unsubscribe from relevant pub sub-channels. Handling hotspots and nearby strangers. Users with many friends, celebrities, or influencers can become hotspots. To manage this, we ensure consistent hashing distributes channel load evenly. For users who want to see nearby strangers, we use a geohash-based pub subsystem. Each geohash represents a region. When a user moves, their location is published to that geohash's channel. Clients subscribe to their current geohash and the 8 neighboring ones to handle border cases. This allows for scalable proximity detection, not just for friends, but for any user in a local area. Key takeaway. This architecture emphasizes low-latency delivery of location updates at massive scale, efficient CPU utilization, and flexibility in handling both friend and stranger proximity use cases in real time.